Welcome everybody to the training seminar tonight on radar and satellite interpretation. I'm Jarrod Schoenecker. I'm on the board for Metro Skywarn. I'm a trainer with them as well. I'm also the president of the Twin Cities Meteorological Society. And Matt, who is going to be our presenter, who put the presentation in this extra training together, will talk a little bit about himself. So without further ado, Matt's going to share his screen and he will introduce himself. So thanks for showing up, everybody.
I'm Matt Taraldsen. By day, I manage the air quality forecast program at the Minnesota Pollution Control Agency. So I do air quality meteorology. From Minnesota, originally from Duluth, went to St. Cloud State for meteorology school and then the University of Minnesota for master's. I'm a former Weather Service meteorologist in Duluth and Anchorage. And then I was an instructor down at the Warning Decision Training Division in Norman, Oklahoma. And that part of the Weather Service is where all the new hires go once they're hired into the federal service. And they do 400 hours of radar training, and then they're certified to issue warnings. So a lot of what you'll see today is taken from that curriculum, made to be a little bit more approachable. But yeah, I've been doing spotter training for several years with Metro Skywarn. Kind of keeps me busy outside of work. I really like weather. So yeah, it's a little bit about me. If you have any questions or anything later, by all means. And also a shameless plug, I'm also the vice president of the Twin Cities Meteorological Society. And so if you're really into weather or you're a meteorologist yourself, we're always looking for people to join. It's a good cross section of people. And so some shameless self-promotion right here too. So what I'll be talking about today is just kind of an overview. We'll start with a little bit about how radar actually works, and then a lot about what different features look like on radar. There'll be some time for question and answers. The second half is shorter and a little bit more qualitative, but introduction to weather satellites, a lot of weather satellite pictures, a few words about weather apps, and then time for question and answer at the end as well. So without further ado, the purpose of putting this talk together was really to get you familiar with radar and satellite, because so many people have apps in their pocket and are using radar either in their day-to-day life or when they're out spotting. I felt it was important to have this talk. And so this will highlight some of the ways that data is used with radar meteorology, but also highlight why spotters are still important and why human eyes are very important in the warning process. The goal really is to kind of demystify how severe weather is detected and how warnings are issued. There's a lot that goes into it, a lot that the radar and satellite technology can tell us, clues as to what's going on in the storm. So hopefully this will kind of demystify some of that, but it's still really important to respect severe thunderstorm and tornado warnings. If you're in a warning, take shelter, respect the warning. There's always things going on behind the scenes at the National Weather Service that you won't be privy to. You know, there's all sorts of spotter reports coming in. They're talking to law enforcement. There's multiple models and all sorts of data feeds they're looking at. So if you are in a severe thunderstorm warning or a tornado warning, and even though you don't think it's happening based on your interpretation of the radar, it's still important to respect those warnings. One part of this whole warning process that I won't talk much about, but is a really important part of it, is that most of the time as meteorologists going into a severe weather event, we will usually have an idea in our head about how storms will look and how storms should behave. And so radar is kind of either making or breaking that mental model. And there's a lot of forecasting, we call it mesoanalysis, that goes into building a forecast and going into warning operations before storms even form. And so this won't cover that, but this is just another reason why severe weather warnings are important. You should respect them. And there's a lot of meteorology that goes into forecasting severe weather before storms even form. And that's a little bit beyond the scope of what I would talk about today, but it's still a very important part. So again, respect severe weather warnings. And one thing I've seen on social media is that people actually message the Weather Service to be like, hey, I see a hook echo. Why aren't you issuing a warning? This class isn't designed to do that. It's kind of designed to demystify how warnings are issued and what kind of clues we can see as meteorologists on radar. It's not meant for you to kind of, do the Weather Service's job for them. They're very good at what they do. They have a lot of training, and hopefully this will kind of shed some light on that. So So before we kind of dive into how you use radar, let's talk a little bit about how radar works. And so um, radar meteorology is really complex. Actually, I took this from the Weather Service in Duluth because I really like it. Um, Radar is constrained by a bunch of different equations, um, and it's complex. There's a lot of things that go into it. And so this is going to be more of a qualitative view of things. We're not going to talk a lot about math or anything, but just realize that a lot of what's going on with these different types of radar products um, are driven by a bunch of different algorithms and equations and everything that go into it. And so it really is a pretty cool piece of machinery, but there is a lot of math that goes into it. And so I'm doing the best I can to explain it in a way that's accessible. But yeah, just know that's kind of the nuts and bolts of the radar. So radar stands for radio detection and ranging, and basically it is a antenna dish that will transmit a pulse of microwave energy through the atmosphere. That pulse is then fired out and the radar will then listen. The radar spends over 90% of its life listening for sound instead of transmitting it. The return energy will bounce into something up in the sky, whether that be meteorological or non-meteorological, and then pushes some of that power back to the radar, and the radar can sense that. Weather radars are tuned to the size of hydrometeors, which is things like snow crystals, raindrops. There's different radars for airplanes, those types of things. They have different wavelengths that they use to do that. But that's basically the nuts and bolts of how the radar actually works. The Weather Service radar fleet was upgraded about 10 years ago to a dual polarization radar. So instead of sending out one pulse in the first example, the radars are actually sending out two pulses, one in the vertical and one in the horizontal. The point of that is that you can then have an X and a Y plane of radar data, and that's super helpful to decipher what you're looking at up in the cloud. And so it allows radar to see the shapes of the objects, and it can differentiate between snow crystals, raindrops, hail, giant hail, and even things like non-meteorological scatterers. So things like birds and bugs and all that kind of stuff. The radar can see that. And because you have this height information, you can kind of siphon out what is actually meteorological and what is not. And that turns out to be really handy. Radar itself also tilts. The radar can be configured to a lot of different options. This is the volume covered patterned VCP-12 severe weather mode operation. And so the radar will start, about 0.5 degrees above the horizon and tilt all the way up to 19.5 degrees. And you notice that there's this area here called the cone of silence, where the radar can't see directly above it, but it can fill in a lot of the gaps. And so that's how the radar scans. It tilts all the way up and it lets you have a kind of a 3D picture of the storm. I also highlighted this 0.2 slice. The Duluth radar got updated a couple of years ago to have a 0.2 slice because it's sitting up on the hill in Duluth, and so it gives better coverage to northern Minnesota, northern Wisconsin. The radar fleet that's out there is the WSR-88D from 1988. Was the original field date of this. They kind of just look like a giant golf ball on a tee. There's one in Chanhassen as well. This is the example in Duluth. But these are kind of the bread and butter of the Weather Service fleet. They're the long-range radar. They have a range of about 290 miles, 140 miles for velocity. Originally, they were supposed to be fielded for 25 years, but they've been pushing the deadline back as they've been adding new components. And so there's still a couple out there that need to have their new components put in, but that will extend the life into the 2030s of these things, which is kind of incredible. It's been around for a while. In terms of what's under that dome, the dome itself is constructed of a polymer that's invisible to radar energy. So the radar energy just goes right through it, doesn't stop anything. Then it has a tower with a pedestal and then a big dish. And so as they've been going through and doing refurbishments of the different radar and adding in the new technology, you get to kind of have the sneak peek. This is from Aberdeen of what the radar looks like taken apart. In terms of the big sites, the radar sites that cover Minnesota, we have the ones here. Most of these are co-located with a Weather Service office. Not all these. Mayville rather is separate from Grand Forks, but otherwise they're mostly with Weather Service offices. In terms of that coverage, Western Minnesota has a little bit of a radar hole, and that's another reason why spotters are really important, especially west of the Twin Cities. The radar beam coverage is well above 10,000 feet. So that means that you can't see anything below 10,000 feet inside a thunderstorm. Northern Minnesota also has the problem. Of course, there's not a lot of people that live in Koochiching and Lake of the Woods counties, and that's why there's a little bit of a gap there, and you can use Canadian radar to fill that in. But those are our two areas of kind of poor radar coverage in the state. And if you ever see severe weather in those areas, reports are extra handy because of that. Some apps also have what's called super resolution radar. And what these are actually called terminal Doppler weather radars, or TDWRs. And these are FAA owned specialized radar for wind shear for airports. And so they detect wind shear, changes the wind with height for airports so that planes can fly safely. We have one at MSP, it's out in Woodbury. It's really high resolution. It only covers 56 miles, but the fidelity you get on it is much better than the 88D. But the trade-off is it only goes for a little bit. And so we're really lucky to have one here. There's mostly in the Eastern United States has them. They're pretty handy. In terms of what that actually looks like, so this is the terminal Doppler on the left, and this is the 88D on the right. This is from the Weather Service office that covers Charlotte, North Carolina, but you can see the fidelity in here. You can make out the hook echo really well. You can see all the parts of the storm. And then over here on the other one with the 88D, looks kind of like pixelated blocks. So just examples of different, if you have one close to you, if you have a radar app that can use TMSP, the terminal Doppler, can give you a better picture right in the Twin Cities metro. Another question I get asked a lot is, how do radar mosaics work? And should I be looking at single site radar, or could I just look at radar in general? If you look at a map of radar over, a wide area, right, like the entire state of Minnesota or over the entire country, basically what's going on is that the vendor that made it took all the different radars in the country and stitched them together, took them from spherical coordinates that they're originally in the Cartesian coordinates and sandwiched them all together and interpolated. And so you get a nice, clear, constant image, but the layers will be different than any one particular radar site that you see. So it's kind of, you lose a lot of fidelity. It's great if you're just looking to see if it's going to rain or something, but keep in mind that, certain signatures can be erased in the radar mosaic. And a lot of apps have this where you can kind of just scroll all over and you automatically get radar data, and it's not a single site. It's all kind of stitched together. So that's a word to the wise. If you have a radar app that lets you grab site-specific data, so just Chanhassen or just Duluth, I always say go for that, because radar mosaicing is tricky. It can erase signals that can be useful. And a lot of private companies that do this have their own ways of doing it. So there's not even really a clear methodology. So that can be tricky. So just a word to the wise. That's how these radar maps are made. And again, you can lose a lot of good data. So that was a quick and dirty overview of the radar technology. And now we're going to pivot into actually using weather data and looking at storms. So the radar image that you're most likely familiar with is reflectivity. And so this is the default radar view. This is the one the media uses. And all this is showing is the intensity of the radar energy, which is decibels of Z, Z being radar energy, that's returned to the radar after bouncing into something in the sky. And so the brighter colors in this example just means more energy returned. And so the way to kind of think about this is that the bright colors usually mean large raindrops, hail, can be debris, all sorts of things. But the brighter the colors, your eye gets drawn to that. That just means it's bouncing off to something big in the cloud. And that's important. The other thing that I love about this is you can see fine line things like this gust front here, all sorts of cool stuff, but that's how this product is made. There's also composite reflectivity. This was developed for aviation. And this one's kind of tricky in that it uses all those different tilts of the radar, and it will show you the highest value in any of those bins. And so that seems really weird because you're looking at kind of a Frankenstein's monster of radar data, but this was built for aviation. This was built for the FAA, and the FAA wants to know what the worst is in that storm, no matter what, at any level, because an aircraft can be at any level. And so they care about hail aloft just as they care about hail at the surface. And so often if you look at composite reflectivity, it'll run a little bit hotter, it'll be a little bit warmer, because usually higher up in the atmosphere, there's probably some more changes to hail or changes to snow that happens and the radar picks it up. So this is an example here. Right in the middle here, you can see how the composite reflectivity on the right is definitely a little bit more, more intense colors compared to the one on the left. And again, that's usually caused by the transition from the atmosphere from liquid rain to snowfall. That'll give you the kind of the maximum reflectivity. Another thing that you probably have noticed before and you might not even thought about is ground clutter. So a lot of times, especially at night or during a warm summer day, you'll kind of get this weird blob that sits out by radar sites. And this is what's called ground clutter. And so when the winds are really calm, especially in the morning and at night, the radar beam will go out and it will hit bugs and debris, little dust particles, all those types of things that are really close to the ground because the wind's not, mixing them out. The radar sees it and you end up with this little kind of blob. You can also get these from temperature inversions. And so again, at night when the ground starts to cool and the atmosphere is still a little bit warmer, the density of the air the changes of the density of the air, I should say, can cause this bloom to show up. And likewise, during warm summer days, when the atmosphere is getting ready to kind of lift and produce thunderstorms, you can get these kind of signatures too. So a lot of vendors, radar vendors, will get rid of them, but they actually can be kind of handy for severe weather. And so that's what actually makes those. Ground clutter can also be really useful for identifying bugs. So this is an example from La Crosse. La Crosse radar sits right above the river bluff. And this right here, these are not meteorological targets. This is actually a mayfly hatch. And so you can see thunderstorms down here, these bright colors, and this northerly propagating blob. Those are mayflies emerging from the river and then going north away from the rain. So you can see all sorts of stuff, sometimes lots of bugs. La Crosse is known for having this. You can see it sometimes in Duluth too. But yeah, ground clutter, so for meteorological purposes, usually isn't all that important, but it can kind of give some clues as to what's going on in the atmosphere. Using radar reflectivity. So again, you're kind of naturally drawn to the brighter the colors. That could be hail. But you have to remember that even if you don't have bright colors, you're going to have maybe some small hail, but you're definitely going to have lightning. So the rule of thumb we tell people is, or I tell people, is that if you have that yellow or warmer color, that you have to be mindful of lightning. And then the hail core, usually the whites, the pinks, those types of things are a good indication that there might be some hail, but it's really hard to just look at a storm and be like, yeah, that definitely has hail in it. But the brighter the colors, the better chance of that. I love this example here because this fine line is also the gust front of the thunderstorm. So as the wind is kind of pushing out of this complex, it will pick up, again, dust, bugs, birds, and the radar will pick that up and you can kind of see that fine line and the clearing behind it. So this would be something to keep an eye on if you're out spotting. Storms can and often do fire along that gust front, or that gust front can move over an existing thunderstorm and kind of change what's going on inside of it. So sometimes even very fine details can be important. Radar and lightning, I kind of covered on this, but 40 dBz, a yellow in most color palettes, that's generally when you have to start thinking about radar or about lightning strikes. Lightning's tricky because unfortunately in the United States, the lightning strike data is proprietary data. And so that's why it's really hard to find an app that will give you lightning data. That's changed a little bit in the past couple of years. The new NOAA satellite can detect lightning flashes in the cloud. And so that is what some apps use to give you heads up of lightning in your area, even if you don't hear thunder. That's because the satellite's seeing that, but the actual true cloud to ground strikes, that data is considered proprietary. And so if you don't pay for that data, you can use, again, the quick and fast rule of thumb of yellow, be on the lookout for lightning. And in this case, it's an area about 300 by 200 miles that's at risk from lightning strikes in this. So can sometimes be very expensive if you don't have that other type of data. Another really common radar product, and this could be a whole talk on itself, converting radar information to radar estimated rainfall is a really kind of mathematically complex process, and there's a lot of different ways that this is done, but it's really handy for trying to figure out what's going on with flash flooding, or in cases like what's going on now with spring snow melt. Any rain that falls over the basin can contribute to flooding. And so 1 hour, 3 hour, 6 hour, 24, and then storm total hours, the radar will just keep adding the rainfall rather, totals until it doesn't detect any yellow anymore, and then it will reset. That's how you get the storm total. And so this is complex. I wanted to mention it because it is important. It could really be a talk all on its own. There's a lot that goes into it, and it can be really handy. And with the dual polarization radar, things have gotten a lot better. These used to be kind of iffy before the upgrade. Now, after the upgrade, they're pretty good because they remove all the hail contamination. So hail. Let's start with hail. Hail is actually really hard to forecast. And so just because you see it on the radar doesn't necessarily mean it is falling. So generally you need that 60 dBz in this color palette, that is that white, and then 65 is pink. It will depend on what app or what source you're using. But generally when you get above that 60 kind of rule of thumb, that's when you have to start thinking about hail. It's really hard to decipher damaging hail, which is just a couple of really big stones, as opposed to a whole bunch of little stones, especially if you're only looking at one slice of the radar data. And so the radar, especially at the surface, will look at a couple of golf ball sized hailstones, and it will look almost identical to a whole bunch of dimes and nickels size hailstones. And so that's a really tricky thing that the Weather Service has to deal with. And again, you get to kind of around that by using all the different slices of radar data instead of just the one. Get further up in the storm and kind of see what's going on. So this is an example of two different storms, both fairly close to radar sites, but which one of these has damaging hail? So on this example on the left here, this one is dropping 4-inch diameter hail, softball size. And the ones here by Duluth, this one's dropping dime size, and these two are dropping nickel size. Now these all look pretty much the same, so what's different? And again, I talked a lot about the slices of radar and why it's important. What's going on further up into the updraft of that thunderstorm is really going to drive what kind of hail falls. So the cell right here that was producing dimes, you can see really only goes up about 5,000 feet. And yeah, it's intense, but it's just not very tall. So there's not much going on. Where this storm is getting a little bit taller, but this one here, it reaches the edge of where the radar can see. Again, the radar can only see 20 degrees above the horizon, which is about 25 to 35,000 or 25 to 30,000 feet in this case. But you have those colors all the way up to that 25,000 foot margin. And so that's how you end up getting really big hail. And you only are going to see that if you either use a slice like this or go up and looking at the tilts in the radar. And so it's really handy. You know, we forget we live at the surface, and so we kind of forget about how this all plays out in 3D, but using 3D is really handy for nailing hail and trying to figure out if what you're looking at is a lot of little hail or potentially big hail. Again, the brighter the colors, the higher, especially where it's well below freezing. This is big hail, where these whites in here are probably melting hail or hail with rain because they're lower than that 10,000 foot freezing level. The full cross section, so a full mature thunderstorm well away from the radar, this is what it will look like, and it's a full 3D cross section. And so I love this example because the actual echo tops are well over 60,000 feet. At the time, the storm was producing 2.5-inch diameter hail, which is around tennis ball size. And so you can see down here, 58,000 feet is the top of that. And we talk in spotter class about the updraft of the thunderstorm, and I actually like here that you can actually see that. So this little nub up here, that is the actual top of the updraft. And the hail producing zone is right here in the updraft. And then the hail falls out into the downdraft and comes down to the ground. And so the actual hail threat for the storm is going to be over here as opposed to over here, but you can see how that process works in real time when you're looking at the thunderstorm. It's pretty cool. And so just a really great example from, this was from central Minnesota, taken from the Chanhassen radar. Another handy thing that you might see are hail spikes. And so when you have really big hailstones, the radar energy will actually bounce off of those hail and bounce on the ground, and it confuses the radar, and it thinks that there's more echoes down radial, so away from the radar, than there actually is. And so you end up with this weird spiky looking thing. And depending on how much the beam is obstructed, depends on really how long this spike will be. But you have to have large hail in order to get the signature. So this is an example of a storm that has that very clear signature. But again, it's dropping golf ball size hail, but this is out in western Minnesota. And so it's really hard when you're this far out from the radar site to know how much of this is actually getting to the ground before melting. But at radar height, this is a really good indicator that there's hail in that storm. And again, probably severe hail. But you have to remember that what the radar is seeing, there's a lot that can happen before it hits the ground. So on a really warm summer day, that hail is going to melt on the way down. And so just because you see this spike aloft doesn't mean it's getting to the ground, but it's definitely something to watch. Another common reflectivity signature is bow echoes and squall lines. And these are super common in Minnesota, especially overnight. We get these all the time. This is an example of a derecho from 2017, storms that fired in South Dakota and then grew into a squall line and made it all the way over to Lake Michigan. This bowing segments in here, these are the ones that will produce damaging winds. And this particular storm had multiple bowing sections. So you have one right here, one right here, one right here, one right here. That bowing shape is caused by the downdraft of the thunderstorm surging out in front of the storm, and the radar then could detect that, but it also draws some precip away from the back edge. And so that's why you end up getting this kind of clear slot. As the wind gusts out, it pulls the precip with it, and that's why you have the gust front. This bow echoes and squall lines can have tornadoes embedded in them. We talk about that in spotter training, but I just wanted to reiterate, these things can be gnarly, but that's what the shape is. But keep in mind that especially when you have kinks and such in the line, that you can have tornadoes embedded within that thunderstorm line. This is an example of a very powerful, mature bow echo pushing towards the Duluth area. I really like this example because it's like textbook of what's going on. So you can see kind of the broken line down here. It's not as strong, and then the really intense line. And you can even see little showers kind of forming along the leading edge along the gust front. Really cool storm, and I like that it's really close to the radar too. But you can see the clear slots back here. That is a clue that these storms mean business. You can see one up here too. It's drawing that in, drawing the air in. And when that happens, that means that the updraft is intensifying. There could be damaging wind. The apex of the bow is the most dangerous part. And again, this clear slot in here is called an inflow notch. That is where the updraft is intensifying and where damaging wind could occur. So in this particular case, you have one here, you have one down here by Cloquet, and you might even have one down by Sturgeon Lake. So the areas in here at the apex of the greatest risk for damage, and then again, those rear inflow notches. You might think, oh, it's fine there. It's going to be good weather, but these are good indicators that something's going on in this thunderstorm. And you have to really pay close attention to it because it's probably going to produce damaging wind. The line further to the south, you can see here, it's very, the colors are very solid, very bright. There's no breaks. As you get further to the south, this broken line kind of appearance where you have spaces of green between the yellow. That means there's weaker cells. There's likely less of a wind threat down there. Those really, when the colors are really very consistent over a wide area and you have this signature, this is a real, slam dunk for severe weather. This particular example is from 2016, produced 103-mile-an-hour wind gusts in downtown Duluth. There was actually a boat trying to go through the aerial lift bridge at the time, and videos on YouTube of it, struggling, and it made it through. I don't know how, but yeah, very powerful storms and a great example of what a really intense squall line will look like. The supercell is the other one. We talk a lot about this in spotter class. Supercells have rotating updrafts. And these types of storms are the ones that are responsible for nearly all the strong and violent tornadoes and basically all the hail events that are greater than golf ball size hail. These will have rotating updrafts, and that rotating updraft allows hail to travel longer inside of it. And obviously, because it's rotating, you can produce tornadoes. The key to having a supercell, and the thing to look for in a supercell, is a hook echo. So in this case, I'm getting a little bit ahead of myself, but in this case, the storm is moving this direction. The upper level wind is pushing the precip downwind. These storms can kind of wrap themselves up and take a little bit more of a right turn, which often happens. So that's something to keep in mind, and especially if you're out spotting. Here's where the downdraft is, where that hail core is. And here's that rear flank downdraft, this little fine line here. And then the hook echo is really the giveaway to what produces a supercell. So what's going on here is that precipitation is wrapping around that updraft. And as that happens, it creates kind of this little hook thing. And this blue feeder area in here, that's the actual inflow of the thunderstorm. So the thunderstorm itself is still eating really nice, warm, juicy air. but that hook just means that that updraft is rotating and kind of coming in that way. This is the 2008 Hugo EF3 tornado. Absolutely picturesque supercell. But yeah, the hook echo is something to keep an eye on, and it's kind of the big giveaway to looking at a supercell. Hook echoes are formed, again, I already talked about this, about the precip wrapping around. And so it might be a precursor to tornado development. You'll see a lot of hook echoes, and most of them do not produce tornadoes, but basically all the storms that do produce big tornadoes will have hook echoes. So this example here is the 2013 Moore, Oklahoma tornado. And you could see it's, here's the hook echo right here. The actual tornado is right in here. It kind of gets that blob looking thing in the updraft. That's all the debris being wafted, but that's the hook echo here. And you can see the storm that was to its south even tried to do that, create a little hook echo too. It was rotating a little bit. And so when you see a hook echo, think of yourself, okay, this is a supercell. The storm has the capability of doing some pretty significant things, but just because you see a hook echo does not mean there will be a tornado. It's just something that happens in supercell thunderstorms. And then this is a good example of why, I don't get too worried about hook echoes. So in this particular example, this is a tornado producing thunderstorm. It's so far away from the radar that you can't see the hook. And so it kind of has this gradient going on, but it doesn't look like there's much going on in here. But the storm at this time is producing an EF4 tornado with 170-mile-an-hour winds. And so just because you don't have a hook doesn't mean you can't have a tornado. And likewise, just because you have a hook doesn't mean you're going to have a tornado. But that's something to keep in mind on, and again, something you can look at and see and be like, okay, I know what that is. Radar ranges also mean a great deal of, make a great deal of difference in how you're looking at radar. So this is that storm that eventually went into Duluth, one looking at the Duluth radar and one looking at the Mayville radar. And so you can see both radars are showing about the same things, but you can see is the radar beam, and then in this example, the radar beam from Mayville has to travel through all this rain to get to here. And so by the time the radar gets to that area, what it's sampling is significantly less than what the radar in Duluth can see, because the radar in Duluth doesn't have to work through all that precip to get that. And so it's really important when you have thunderstorms that move, or if you're out mobile spotting, to keep that in mind, that there's different radar sites. You want to dial into the one that's closest to you. And this is a good example from the Warning Decision Training Division about how a hook echo can kind of get obscured. So this is a storm that's producing a tornado. The radar site's right here. And so that storm is producing that hook right there. But in this example, looking at a different radar site further away, it gets obscured. You can't see what's going on. So the reason for that is as the radar beam gets further away from the radar site, the pixels kind of get larger and larger and larger. So you lose fidelity one way, and then the radar beam also gets degraded as it goes through rain. Every time it picks up these signals, obviously some of that power that can go on from there gets reduced. And so when you have this example here on the right, all of this rain behind this line, I don't know if I would trust the Duluth radar or the Mayville radar. I'd probably have a better view just because it has to go through this big line to get that information. So that was all about reflectivity. Now we're going to pivot a little bit to the Doppler part of Doppler radar. So not only can the radar determine how much power is being transmitted back, but the change in the frequency that the radar detects the energy coming back can tell the radar what direction targets are moving in relation to the radar. And so, well, okay, what does that mean? That means that Doppler radar can detect changes in wind inside a thunderstorm. And this is actually how tornado watches, or tornado warnings rather, are issued, is through this, using this product. And so for Doppler velocity, again, reflectivity is all like, oh, the bright colors are bad, but in velocity, it's completely different. The green represents targets that are going towards the radar, and the red means targets are going away from the radar. And so this big blob of red here just means that you have targets moving from west to east. This gray line you see here in the middle, that's called the zero isotop, which is the 0 degree velocity, and it usually runs, basically perpendicular to the radar site. But in this example, the wind is flowing from west to east, and so it's going right through here, and the isotop represents 0 right through there. You'll also notice this purple we call it the purple haze. But as the radar tries to figure out which way things are going, it kind of hits a sweet spot where it gets confused, and the algorithm that actually creates the velocity product will break down. And so you'll see this kind of in a big circle as time around the radar site, and it's just the area that the radar has a hard time resolving the velocity. And that really sucks when this purple happens in an area where you're looking for a tornado. But in a nutshell, that's how you read velocity data and how it works. So what a tornado will actually look like on velocity right here is called a couplet. And so here the radar site is to the south of this. And so green going towards the radar, red going away. And so there's rotation in here. And so the radar itself is not seeing the actual tornado, but if you have a pen in your hand and you move your hands away from one another, what happens to that pen? It'll start to rotate. And that's what's going on here. So the radar will observe the updraft rotation, the parent circulation of that tornado, not the tornado itself, but this is what a tornado will look like. And so again, here's a little bit of a hook echo. It's pretty ill-defined. This is an EF0 tornado. You can see the couplets right there. Hook echo, again, not very well defined. But the velocity is what you use to detect rotation inside the thunderstorm. And yeah, I always remember red away, brake lights of a car away from you, that type of thing. That's how you read velocity. And so green's going towards, red's going away. And when they combine like this in this tight little area, that's a cause for concern. Doppler velocity is also really good at detecting damaging winds. And this comes with a big caveat, because the radar is only going to measure the magnitude of the wind that is coming towards the radar. So I use this example here because the storm is moving basically almost perpendicular, almost directly at the radar, I should say, almost a 90-degree angle. And so the radar is sampling all of this really well. There's not a big angle that would diminish the returns. And so this is an example here of 100-knot winds, 115 miles an hour, 785 feet off the surface. This is that same storm I showed earlier that produced all the wind damage. And so the velocity is really good at picking that up. But you have to remember there's angles that go on to this. And so if the storm moved over the radar, you might not see anything for a bit, as the radar is only measuring the winds coming towards or away. So if you're at an angle, use that with a grain of salt. The other thing to keep in mind with damaging wind threats from thunderstorms is that this is what's going on at radar height. And so you can have, and I've had storms that have done this, really good velocity presentations, but at night when the ground is cold and there's this kind of wedge of stable air under it, that wind cannot punch down to the surface. We call them elevated thunderstorms. And when that happens, even though you might have really good velocities, the wind just won't hit the ground. And so that's one of the reasons why getting wind reports is really handy from spotters, is because we as meteorologists have a hard time accounting for that. We know it happens, but we don't know if a thunderstorm can break through that or not. And so, this is an example here, 785 feet up at 100 knots, it's probably going to produce very severe wind. But that's another reason why calling in those reports are helpful, because it kind of lets the forecaster know how much of what you're seeing on radar is actually getting down to the ground. Yeah, so can that be repeated and reinforced why winds won't get down to the surface on an unanswered period? So at night, when things get cold, the atmosphere itself doesn't cool as fast as the ground does. And so when that happens, that cold, stable air that's next to the ground basically is like a pillow. And so if you have wind above it, it has to punch through that pillow to get down to the surface, that stable air. And that stable air is actually really good at stopping that from happening. And so a lot of times when you have a severe thunderstorm warning after dark, that might not have any wind in there, the velocity might have that, but just because of the way the atmosphere is set up, that wind will not get through that stable air. And so that's something that's really tricky. And I've seen it on Twitter, a lot of people that see velocity signatures and wondering whether there's not a warning. Well, the answer is because it's the middle of the night, and a reverse cap is a good way to think of it. That stable bubble near the surface is going to stop any type of damaging wind threat or a tornado threat. Also a big reason why we don't get tornadoes in the middle of the night here. We just have that stable ground layer, if that helps. Another really handy thing about velocity that you probably have not seen before, but at the very top of the storm, you can actually look at the storm and figure out how intense the updraft in that thunderstorm is. So this is an example from the North Metro. I kind of cheated here. These are local storm reports, so damaging wind gusts and then hail. But in this example, this is at 44,500 feet, 106 knots. This is about 115 mile an hour wind that is moving, again, red away from the radar. So that's how fast that's going that way. And then we have this green, which is about 33 knots going towards the radar. And so again, with the tornado, you have convergence, you have the colors going towards each other. But for divergence, you have them going away. And why do we care about this? Well, this change in divergence is basically a way to approximate how fast the updraft of this thunderstorm is in real time. You go all the way to the top of the thunderstorm, you look until you basically can't see any green left in the radar, and then take a look at what the winds are doing. And so in this case, there's 160 mile an hour updraft in the storm. That's how fast the winds inside this thunderstorm are moving up. Again, I talked a little bit about that angle. You're not at a perfect angle here. It's about 20 degrees. So you're probably undersampling this a bit. And using the Weather Service's handy dandy chart, when you're in that range, you're probably looking at golf ball size hail, and you can see here's some 2-inch diameter hail reports. That holds pretty true here. And so that's another way, if you don't have spotter reports, this is another way that meteorologists can kind of gauge how fast the updraft of the thunderstorm is. And from a spotter perspective, it's kind of gives you a way to kind of triage what storms are capable of producing the most damage. And so this is actually the anvil of the cloud. The updraft of the thunderstorm will hit the top of the troposphere and creates that anvil, and the anvil will fan out basically the same way that in the same way that the updraft moves. So good correlation between the two. It's pretty cool. So velocities can be messy, and storm systems can be really messy. And so I always tell people respect warnings, because some situations can be really tough. And so this is an example from Oklahoma. This is a squall line of thunderstorms, sort of, but we call it a quasi-linear convective system, or QLCS. And so in this particular example on the left, the reflectivity, all these little notches that you see here, those are all tornado vortices. You can see in the velocity here, I love this one. Oops, I went back too far. You could see there's multiple tornado vortex signatures in this. And so you have the one up here. You have one that basically goes right through Tulsa and develops right in the middle of the night. This type of stuff, it can happen in Minnesota. It's more rare, which is why I have an Oklahoma example. But, this is why sometimes you get these tornado warnings that are really over a wide multiple county area. And it seems like, well, why are they doing that? And the answer is there's not a really other good way to warn in these types of situations. When you have these types of circulations all stacked on one another, the risk is just too big of a tornado to try to put multiple little boxes out and everything. And the Weather Service will try to do that, but it can be messy. And so that's why we always tell people to respect the warnings. These things can spin up really fast. And by the time you see them in your app on your phone, it's a couple minutes delayed, and the Weather Service is already on top of it because they get the data right away. So respect tornado warnings. It's a good message there. So I talked a little bit about dual polarization radar a bit, and this is going to get probably into the weeds, maybe more than you ever wanted to know about radar, but we're going to talk about it anyway. And dual polarization radar has really kind of been a game changer because it has that X and the Y pulse. You can start looking at the shape of whatever is in the clouds, whether that be debris from a tornado, whether that be giant hail, whether that be small hail, raindrops, snow crystals. They'll have slightly different properties. And so the different dual polarization radar products are listed here. Differential reflectivity is basically the X versus the Y, so the height versus the width. Correlation coefficient detects the consistency of the shapes within the radar beam. And KDP, specific differential phase, detects liquid water. Of these ones, you probably have never heard of one or three, but correlation coefficient has kind of been a rock star, for lack of a better way of putting it. But the media will use this a ton when they're doing tornado coverage to show where there's actually debris being lofted into the updraft of the thunderstorm from a tornado. It's really handy for that. And so I'll talk a little bit about the other products, but correlation coefficient CC is really the one that you'll probably hear the most often, and it does give the capability of seeing tornado debris being lofted in real time, and you could issue a radar confirmed tornado warning. Social science has proven that people don't react as strongly to that wording as they do from a spotter indicated threat. But it's nice to have that capability, especially in the middle of the night when you have a storm where people probably can't see a tornado. Even if it does occur, you can see that debris being lofted and issue that warning from that. So yeah, we'll talk a little bit about each of these. And so correlation coefficient basically measures how correlated whatever you're looking at in the cloud is. And so in this example here, the blues are poorly correlated things and the pinks are highly correlated things. And so it just so happens that rain and hail and Graupel, all the different types of precipitation in the cloud basically look the same to the radar. And so that's how you end up getting these pink areas and areas that it's actually raining. And then you get the blues in areas where it's ground clutter or something else. So this can be really handy, not just for looking at tornado debris, but trying to figure out like what's going on down here. Is this actually like a storm developing? And you look at the correlation coefficient, you see the blues, low correlation. This is biological. So this is bugs and stuff being picked up by the radar. You can also see kind of the suppression up here by Lino Lakes, where there's bright reflectivity, that the correlation coefficient kind of takes a dip. And that's because you're getting kind of into this giant hail range where you have either large wet hail or even just giant dry hailstones. And so correlation coefficient, again, really good for determining radar or determining what you're seeing on radar is meteorological or not, and can see debris from a tornado, but it also can be useful to kind of look at and see if you're seeing really big hail or anything like that. It's a pretty cool product. I end up using this one a lot. So different ways of looking at it. This is the same setup again. You can see the blues in this. It also is really good at picking up the transitioning of rain versus snow. So me and my sister lives down in Shakopee, and she was telling me how it's raining at her house, and I was up north and it was snowing. And so I sent this to her. And so this band right here of low correlation is basically the phase change of precipitation from snow north of that line to rain south of that line. And it seems weird that it would show up like that, but you have to remember that the radar beam is going out, away, and higher into the atmosphere away from the radar site. So it shows up as this kind of beautiful band here, and that's the transition between rain and snow. Really handy for winter storms and trying to pick out freezing rain versus sleet, things like that. Again, another, yep.
See, I got a question here.
Yep.
From one of the viewers. They want to know what Graupel is. I figured you would explain that probably best, because a lot of people do not know what that is.
Yeah, so you might have seen it, not even realize what it is. Graupel basically looks like Dippin' Dots or like little styrofoam balls. And what happens is that you have a snow crystal way up in the atmosphere, and it partially melts, and it falls through a layer where you have both liquid water that's ready to freeze and some ice. And you end up getting basically super cold water that condenses and flash freezes onto a snow crystal. So what ends up falling out of the cloud is an opaque little round kind of BB thing. And you can tell the difference between Graupel, which is again caused by flash freezing of objects onto a snow crystal, from sleet, because sleet will come down and basically be a little ice pellet. And they'll both be, sleet can be, it's usually clear, but it can be opaque too. But the difference is that like sleet hurts when it hits you, and Graupel just kind of falls from the sky. It looks like little styrofoam balls. Graupel, because it forms in an environment where you have to have both liquid water and frozen precipitation, it's a good indicator that the atmosphere is trying to turn over in winter weather. It's so whenever you see that, you usually see it when temperatures are right around freezing and things. Yeah, that's what Graupel is. And a lot of people think Graupel and sleet are the same. They're not. Again, sleet is little ice pellets, and Graupel is basically a little ball of air with some frozen ice around it, and it looks more like styrofoam. So I hope that answered the question. So moving on from winter weather, talking about tornado debris signatures. This is a good example. This is the Rolling Forks, Mississippi tornado from just a couple weeks ago, high-end EF4. And so This is the supercell thunderstorm, and these are two different radar views. One of them is looking at the view of the rotation inside the thunderstorm, accounting for the storm motion and without, but you could see really powerful couplet. The radar itself is to the south. So you have the radar circulation here, plain as day, and then you can see there, this drop in the correlation coefficient, that blue, that's debris being lofted. What's even more amazing with this one is because this storm produced multiple tornadoes is that you get this other secondary minima over here. That's actually debris being picked up and being thrown around inside the thunderstorm after it's been in the tornado. It's called debris sorting. And it's another clue that whatever's going on in this thunderstorm is really bad. Big hail can cause this too, but usually what will happen is that you have debris being scattered inside the updraft of the thunderstorm away from the tornado. And so, like I said, this has gotten a lot of traction. I've seen a lot of media people use it live real time. And so that's why I wanted to spend quite a bit of time talking about it. So you can kind of go through the boxes here of like, okay, so this hook echo, that's bad. Couplet, that's bad. And then this is all in the same spot. That's a dead ringer. It's called a tornado debris signature, or TDS. And that's how you can confirm a tornado in progress using radar. Of course, by the time you see the debris signature on radar, the tornado is already in progress and might already be done. So, you know, it's not one of those things that you can use to predict tornadoes. That's what the velocity is for, but it's a way you can confirm one that it's doing damage. So a thing that I was debating if I wanted to put this in this talk, but there's been a lot of, seen a lot of back and forth on Twitter about how we can estimate tornado intensity with radar. And this is from a paper by Justin Gibbs and Randy Bowers, former Norman forecaster and WDTD instructor. Basically, we do have some skill now where we can actually look at the strength of the rotation inside of a thunderstorm along with the height of the debris signature and get some idea, or at least have some skill into what type of a tornado is occurring. And so this has allowed the Weather Service to issue what's called tornado emergencies, which are for very large, probably violent EF4, EF5 types of tornadoes. It turns out we do have some skill with that. And so this is using that debris signature in tandem with the velocity to really drive that home. And so it's a new tool that the Weather Service is using. Like I said, the research has been pretty good, and it does give credence that you can start to differentiate a weak tornado from a strong or even violent tornado, which is pretty cool. The debris signature can show up in even weaker tornadoes. So this is an EF0 tornado. It's not too far from the radar in Chanhassen. You can see it pretty clear as day, that dark blue and the correlation coefficient next to that couplet. This is one here where you have the reflectivity, the couplet, and then not as pronounced of a debris signature, but it's still there. And this is up in Elk Mound, Wheaton, Wisconsin, so pretty far away from the Weather Service in Chanhassen, and that's why it looks kind of more pixelated. So some good examples of what that looks like. I already kind of showed a 3D representation of what reflectivity looks like, but all of these other products can do the same thing. So going back to that Rolling Forks, Mississippi tornado, as the tornado went through Rolling Forks, it was lofting debris to about 39,000 feet, which is astounding. That definitely puts it in the echelon of either high-end EF4 or EF5 range. And we kind of knew that in real time as it was happening, that this is a really bad situation. As the storm produced more tornadoes down the line, it actually got to the point where there is debris being detected on radar falling out about 18 miles away from the tornado. And this was actually correlated with ground reports, people reporting papers and things falling out of the sky. And so some phenomenal things you can see on radar, but it's like a punch in the gut when you see this types of thing, because you know something bad is happening, especially in this part of the world. There's really vulnerable populations here. And so this was a really gnarly situation, but that's how it looked on radar. Talked a little bit about that tornado debris signature and how tall it is. This is an academic paper, but basically shows that we can also use that tornado debris signature height to determine the strength of a tornado. And so if you have a debris signature of 39,000 feet, you can see you're up here at the tail end of an EF4 plus tornado. And so when that happened, you know, my heart sank because I knew there was a really bad tornado in progress. And it's fascinating that we've gotten to the point that you can look at radar data and kind of get that sense in real time. But that's where the science is. And again, there's some good research about that. So moving on from debris, another handy tool in the arsenal of radar meteorology is differential reflectivity. This one is a little bit strange because it's measuring basically the X versus the Y of whatever you see in the clouds. And so you can see this example here. Snow crystals are really flat, not tall. Hail is basically circular. And then a raindrop kind of looks like a hamburger bun as it falls. It flattens out, and so it's long and kind of fat and short. The end result is that when you combine it with reflectivity, so here's next to Medina, there's this really bright hail core. But on this other side here, you kind of see these warm colors. And these warm colors, you're ending up getting into large, if not massive hail, especially in these green areas. And so another thing that the Weather Service can look at is this shape inside of it. And so when you have the bright reflectivity along with this, it's another giveaway. There's also the specific differential phase, which measures the amount of liquid water in the updraft. This one is interesting in that it can show areas of flash flooding, but it can also show melting hail signatures. So in this example here, my little annotation thing isn't showing up, but you can see you have this hail core here. You have an area in here with these bright colors, which is showing rainfall rates probably of several inches per hour or melting hail. And so some of the hail that you're seeing in here is melting before you hit the ground, before it hits the ground rather. And so it gives you a clue that, okay, this looks really bad on radar, but it might not be a slam dunk because there is a lot of water in there as well instead of just ice. So handy thing to look at. Again, you probably have never heard of this before, or maybe you have, but it's something that really is helpful for parsing out severe hail. So let's put it all together. We have this lovely storm just approaching the Twin Cities metro area, Wright County. You see the bright colors here, all these whites and pinks extending up to 30,000 feet. And so immediately, if I saw something like that, immediately my brain would go to hail, especially with this height here. The velocity field, there's some brighter colors in here, but I'm not seeing any couplets, and I'm not seeing those really, really bright colors, those really intense winds. And so this is probably a hail threat more than anything else. So if you break through and actually look at all the different parts of the different radar aspects, the differential reflectivity is really low here. It's really low through the clouds, and that really low value means that you're seeing something that is virtually circular in size. And so this area here, which is really where that bright hail core is, that is giant hail, where the area down here, these brighter colors, means that there is something that is not circular in the clouds. So that means it's probably melting hail or a lot of smaller hailstones. So this is an easier way to kind of differentiate where a giant hail threat is as opposed to just golf ball size hail threat. Again, that's what that looks like. KDP, looking at liquid water, you can see in this area, there's a little bit of a signature that this might actually be melting hail. Down here, they don't see much of it, so whatever it is, it's pretty consistently dry hail. But looking at 3D, you can see that that little yellow area that kind of is like, oh, it's melting hail, is actually located right at the freezing level, 10,000 feet. And so, again, this indicates that you're probably seeing just a couple pixels of melting hail, but everything else would suggest that you have a really nasty thunderstorm. Finally, looking at the correlation coefficient, you see the darker colors in here that are not maroon. Whatever is falling in there is irregularly shaped and not repeating. So it's probably giant hail tumbling around in the updraft. So the end result was that this storm produced 4-inch hail in Wright and Hennepin counties. As it moved eastward, it dropped golf ball size plus hail in Wisconsin. At this time, it was not much of a wind producer. It did produce wind damage further to the east. And there's no flash flooding and some small hail that fell. But usually what happened is that people who did have hail damage got walloped with the 4-inch hail. There wasn't a lot of smaller hail in there. So that's how it works. So before I take question and answer time, I see people talk a lot about algorithms and different types of radar products that are out there, and you may or may not have heard of these. There's vertically integrated liquid, maximum estimated hail size, the probability of severe hail, and echo tops. All of these are handy and useful, but they all are error prone. you have to take them with a huge grain of salt. These algorithms basically look at all the pixels stacked up on top of each other. And if you have a rotating updraft, that is not a very good assumption because the rotation means that the vertical cross section is not going to be perfect. So the algorithm dies. If you also have a fast moving cell where the updraft is really tilted, the algorithms don't account for that and will really underestimate the hail size. And so you can use these if you're spotting or if you're looking at radar, but just realize that they oftentimes have issues. And just because you see, the probability of severe hail is 100%, doesn't mean there for sure is hail in that. And likewise, just because you see 30%, it just might mean that the storm is super sheared, and the updraft is at a really high angle. And so the algorithm is whiffing it, but the storm itself is producing. So yeah, my 5-cent tips about those. Yeah, so the hydrometeor classification, I didn't explicitly talk about it because it's basically taking all of those dual pole products and pulling them in real time using machine learning. It does an okay job. It tends to really have an issue with big hail in particular. And so a lot of times you might notice that there's like the red, the large hail in signature in there, and it's just because it's the bright reflectivity, and it's actually a lot of smaller hail that's coated in water and looks worse than it is. And so it is out there. I like I said, it's one of those things I use with a huge grain of salt, especially with hail, because really large hail, because it's so irregularly shaped and tumbling around in the updraft, can fool the radar pretty good when you're using these algorithms without actually going through the data itself. So I hope that makes sense. It wasn't too hand wavy. Oh, I always look at super resolution. Digital is something that will probably disappear fairly quickly. They got rid of standard resolution. I think digital is going to be the next one. Super resolution is basically the default way of looking at radar. That I would always recommend looking at that. Sometimes you'll see digital for like digital storm accumulations and things like that. That's using the dual pole products where it's actually trying to measure the amount of hydrometeors being measured, which is pretty cool. So if you see digital storm accumulation, digital storm total, those types of things, it's good. Otherwise, if you see digital in front of it, it's probably more of a legacy product. So like there's digital vertically integrated liquid. It isn't that much better than normal vertically integrated liquid. It just has some slightly different algorithm changes in it. So yeah, I did have that example of a 3-body scatter spike earlier of that hail spike in Western Minnesota. I can go back to that. And so we call them 3-body scatter spikes. Basically, it's just radar energy being scattered. There we go, right here. This spike right here is called a 3-body scatter spike, and that's a good example, a good indication that you have hail, at least at radar level inside a thunderstorm. These vertical cross sections are created with a software I have called Gibson Ridge Analyst or GR Analyst. It's expensive, but it's really handy for meteorology. There's also Radar Omega that will let you view things in 3D, which is pretty handy and available on mobile devices. Yes, Eric points out a pretty good one. So there will be usually a few pixels of dropout right over downtown Minneapolis, and that's because of the big buildings, and they're actually basically perfect radar height. So you have some sort of suppression there where pixels will drop out. What gets interesting is when you have wind around those buildings, the radar will actually pick it up and think they're real returns, and so they'll sometimes get plotted even though they are from buildings. That's why you will sometimes only see them. Sometimes it's because there will be turbulence around the buildings enough for whatever is being picked up with it will move, and the radar will be like, oh, there's something there, and plot it. And sometimes you don't see it. And so, yeah, it's just a manifestation of those buildings and the turbulence around it. You can also see the cars on 94 and 694 sometimes too. If there's a good temperature inversion, it will bend the radar far enough south where you can see the cars on there. And there'll be like a red line right along the highway of 60 miles an hour. Level 2 in radar selection is basically the uncompressed version of the radar data. So there's level 3, level 2. Level 3 will have some of those algorithms in there, but there's also a compression algorithm that is run on them. And so level 3 data won't have the fidelity of level 2 data, but the trade-off is that if you're like out in a car trying to get data using a cell phone, you're using a lot less data if you're looking at level 3 data as opposed to level 2. And so I have GR level 3, which I will use if I'm ever out and about because it's a lot less data intensive, but GR2 level 2 data is the full uncompressed radar information, and each slice is, several gigabytes.
Somebody had a question about what a high precipitation and a low precipitation supercell, what do those look like on radar? And the simplest way I can tell you that is a high precipitation supercell is probably the one you're most used to looking at in examples, where it shows a nice hook around the backside and you kind of have somewhat of a donut shape or a circular shape at the end. That's a high precipitation supercell. If you have a low precipitation supercell, that area of rain and precipitation, sometimes hail that will wrap around that sometimes, is either completely non-existent or it's very lightly wrapping around it. And typically with those, you will see the rest of the supercell structure, but you're going to be missing what that apparent hook-like appearance would be on the end. So you kind of just tend to see, essentially that wedge, where we talked about the eagle wings earlier, that whole wedge of where the main precip is falling and then nothing behind it. There are cases where you have a low precipitation supercell that is missing that precip wrapping around where that inflow area is, and then there's a very strong tornado that's actually picking up debris, and so you'll end up with the low precipitation supercell look, and then you will actually see a small dot of where debris is being picked up and measured in the reflectivity. Good question here about water spouts. So water spouts, that's a tricky one because marine warnings typically happen on large bodies of water. Now, if you're talking about Lake Superior and you have tornadoes that go out over Lake Superior or form over Lake Superior, that area, they would be just considered a special marine warning. How does radar measure echo tops? Radar measures echo tops by looking for the tallest part of the storm that they can see. So any point where it can read particulates in the atmosphere coming back down, that's what it assigns an echo top to. Now, there's an inherent problem with that if you're very near to the radar, because we have that cone of silence Matt talked about earlier, where essentially in normal scans, the radar does not scan real high in the atmosphere. It does have the ability to look pretty far up in the atmosphere, but definitely not directly above it. And usually when we have severe weather, the radar is in an operating mode where it operates on the very lowest levels of the atmosphere only because they're very concerned about what's happening near the ground. And so sometimes even relatively close to the radar, a little bit away from it, you may not get accurate echo tops where it'll say the tops are maybe at 20,000 feet, which might be, where the radar is maxed out.
Oh, here's a good question about there's always a delay. Yeah, so what happens when you're looking at radar data is it's coming out of the Weather Service's computer, going out to an Amazon Web Service cloud that NOAA uses, and then out to the vendor that created the app, and then through your cell connection into your phone. And so by the time you see a radar image on your phone, you're usually 3 to 5 minutes late. And that's just because of all the steps that the data has to take to make it to your phone. And there's no real easy way to get around that unless you have a direct feed to the Weather Service, which not a lot of people have. You can get what's called a NOAA port. Allison House feeds use them. Those will be a little bit faster, but they're not going to be as fast as working at home or something like that, where there's less steps to go through.
I see one question about how does spotter information show up as an overlay. They're using Spotter Network, and spotter network on the radar apps that we've aforementioned can be included as a layer on there. So any individual spotter that either, if they're at home, they have kind of a manual location usually, or using their phone and choose to display their location, will show up on that if you have that, feature selected to be able to be viewed. Which country has the best radar? You mean like the best radar network? I think the US probably has the most coverage for radar of any country, but there are places like Australia, which we do kind of partner back and forth with meteorologists and fire season for, that has a decent radar network, but it's really only where they need it to be, which for them is primarily along the coast because there's a lot of desert and uninhabited areas out there.
I was noticing in that apps slide, you had Radar Omega as Apple. That is available on Android as well. I've got it on mine.
Yeah, I noticed
And
that
Windows.
too. Yep. They've upped their game. I really do like Radar Omega. It's a little bit pricey, but it is handy for the 3D.
Radar Omega, if you subscribe to their services, is also available on your desktop computers, but only if you subscribe.
Okay. In the interest of time, we're going to keep going into the second half, the shorter half, I should say. This satellites are conceptually a lot easier than radar. And I think there's some really cool data. This is also something that in meteorology, it's really a hot button right now, and a hot area of research because we have new rapid satellites. So that one gone up in the past couple of years, which are pretty cool. The main satellites that you see on the news and everything like that are geostationary operational environmental satellites, or GOES. There's basically two different types of orbits that satellites do: geostationary, where they're parked in space and hold their location over the Earth for a certain area, or polar, where they kind of just go up and over and up and over. And so geostationary is nice because they are always there and you can always get data. Polar usually are closer orbit to Earth, but you get data whenever you get data. The first GOES satellite goes back to 1975. We're on GOES 16 and 17 with 35,790 kilometers. These new satellites are capable of 60-second rapid scans, which means you're getting an image from a satellite in space every 60 seconds, or on par with the data that you'll get from satellite, which is why there's been so much research. We're seeing so much stuff that we've never been able to see before, things that we thought were there, and now we can confirm. It's really cool, and that's why there's been so much research about using satellites in weather operations. Yeah, it's crazy that you can pull data from space about as fast as you can get data from a radar, in Chanhassen. Crazy. In terms of what the GOES satellite actually look like, this is what they are up there. They have a big solar panel. They have a bunch of different sensors on them. They can map lightning. The magnetometer is for detecting space weather conditions. And there's these different charts, or these different channels rather, that are basically built for different types of meteorological phenomena. So you have the visible light, near infrared light, and then infrared light, and then even within them, different wavelengths. So this will let you pick out things like snow versus ice, cirrus clouds versus low stratus clouds like fog, picking out ozone, picking out long wave radiation, so you can actually look at dry areas inside of a thunderstorm. A lot of cool stuff, and it really opens up the doors for all sorts of different research and combining these different things. The one you'll see out more often are these visible ones where you're seeing just the clouds from space, and then the infrared ones. These different channels here are the ones you'll see a lot of. And then a lot of times when you're looking at like jet stream and things like that, you'll be talking about the water vapors, channels 6.2 and 6.9, that are pretty good. So that's how basically the satellites are set up. And again, they're taking all of these measurements every 60 seconds and beaming them back. So let's dive into some satellite pictures. And so GOES East and GOES West, there's a question here, basically are just the domains. And so with the Weather Service having offices in Alaska, Hawaii, and then even Guam and American Samoa, Goes west will cover that area out there. They also use it for typhoon warnings, things like that. Goes east is in a geostationary orbit that basically covers the entire Atlantic basin. Goes east is a little bit older, but they're functionally the same satellite. They're built at the same time, just launched at slightly different times because they didn't want to put all their eggs in one basket. So basically, they just cover different sectors. They're the exact same platform, but they're just parked slightly different, so you get better coverages of the oceans, either the Pacific or the Atlantic. Moving on to satellite data. So the first and kind of stereotypical image of satellite data you think of is the visible satellite. So this is an example from 2010, the beautiful low pressure. This is actually the low pressure record holder in Minnesota. This clear area here is called a dry slot, and this area up in here, that's the comma head of the low. So, it's a really beautiful picture, but as a meteorologist, you see the spirals in here, that's the center of the low. You see in here, there's this little dry area, that's an occluded front, and then you can see these bright bumpy clouds. Those are thunderstorms, things going up that are associated with a cold front. So this is what I annotated it very poorly, but this is what it looks like, and what you can use visible imagery for. You can kind of look at the different sectors of the low. It's handy to kind of track how things move and everything. And so this is 2010, the record low pressure for Minnesota, and it's just a beautiful image and kind of what a good example of what you can use satellite for. Satellite's also kind of weird because it's a lot of qualitative, and so a lot of what you're looking at are basically the same you're looking at when you're out spotting. The crispness of the clouds for those updrafts, just as they look crisp and clean when you're out in the field, they'll look the same way on radar. And then when you get kind of these more strung out, drawn out clouds, that's usually a warm front where the lift isn't quite as intense. There's a lot of qualitative and textural things that will go into how you use satellite data, and we'll talk a little bit more about that. Visible imagery is, some of this stuff is just so cool. So I said you had the 60-second updates, and so these are thunderstorms in central Minnesota back in 2020, and you can actually see the rotation inside of the parent updrafts in these supercells, which is, we've never been able to do that. And you can actually see the gravity waves propagating out into the anvil. Really cool stuff. And so basically it allows you in real time to kind of isolate what updrafts look the most intense. You can use radar data and plot it on top of each other. And so you can kind of get a sense of what, out of all the cells you're seeing, is there one that from the top side looks a little bit more impressive or has an updraft pulse that the radar is not seeing. You can kind of fill in the holes with that. And so this is just a really cool example of that you can actually just see the rotation inside of them, which is crazy. Another thing about visible imagery we use it for, it can be for not tornadoes or severe weather. So this is an example of a ground blizzard. So these streaks you see right here is actually snow being picked up and lofted by 60-mile-an-hour winds across the Red River Valley, with visibility of less than a quarter mile in the blowing snow. And so pretty cool example. You can also see the frozen lake, Red Lake over here, Lake of the Woods up here. Pretty cool stuff. So at night, when you're trying to look at visible imagery, it's not going to work because there's no sunlight. So you have to switch over to infrared. And so infrared uses different bands of the satellite, but basically it measures whatever energy is being radiated back to the sensor from the highest point. It seems really weird, but basically this doesn't do a good differentiation between the ground, stratus clouds, or the top of a thunderstorm. And so whatever is the tallest object is what you'll see. It can be kind of tricky when you have a thunderstorm that grows like this one does and kind of covers up the entire state. There's other thunderstorms that are smaller. Under it, you won't see it. But infrared is really handy for picking out at nighttime, picking out updraft pulses. And just like you could see the areas of the most intense updrafts with the rotating thunderstorms earlier, you can see them in here, how there's pulses of updraft in here. And if you're watching this in real time, you can kind of get a sense of what areas of the storm are most likely to produce severe weather. And it's really kind of a great way to kind of ground truth what you're seeing with radar with satellite. And so you can go hand in hand and kind of keep track of things. And so it's really cool that you can see this. And the fidelity of the infrared is not quite as good as visible, but it's still pretty darn good. And again, it's really good about picking up these updraft pulses and the kind of dynamic processes inside the thunderstorm. The water vapor channel, this has been an old standby, but basically dry air, and this is the warm colors, and then the greens are saturated and the blues are kind of in between. And so this is really handy for picking out kind of the large scale troughs and ridges. And so in this case, you have a dry line here in Texas digging in, and you have thunderstorms erupting on the moist side of the dry line. You have a little bit of a disturbance here in the upper Midwest, and then you have this big trough here across the Atlantic. And so this is where the jet stream is, the dry air, where all the air moving is clearly visible. And then with the dry line, it shows up really well in imagery. And so water vapor is handy for that. I see people in the media use this all the time too. It's a pretty handy feature and hasn't changed much through the years. It's just now with GOES-R, it can get the data a lot faster. So getting in the nuts and bolts of severe weather, this image is from a couple weeks ago. This is Oklahoma, this is Texas, just so you can orientate yourself. And this is basically the birth of thunderstorms. We call it convective initiation. And so if you're out spotting, a lot of times you might notice that the Storm Prediction Center will issue watches right before the thunderstorms really get going, and that's because they're watching this. And so these little, what started as cumulus clouds and then kind of just erupts. If you have an area where the models are already suggesting there's going to be severe weather and the parameters are right, and you see this type of signature, these little bubbly cumulus clouds start going into that environment, that's basically the time you need to start thinking about the possibility of severe weather. I also like this example because you can see back here, there's kind of these wavy looking clouds. This is, so there's a front in here and it's trying to lift the air up, and that's what's generating these thunderstorms. But in areas of stable air where the cap is, it actually is fighting against that, and you can actually see that cap mechanism on satellite. And likewise, the low clouds up here do the same thing. And so if you ever see in a discussion about a watch about cumulus fields or convective initiation, this is what you're talking about. And it's basically what you see from the ground, the cumulus clouds that will then rapidly grow. And again, you're combining these visualizations with your knowledge of what you think the atmosphere will be doing today to combine them. So this one is slowed down a little bit so I can talk about all the different pieces going on. This is, again, Oklahoma, Texas. This is a little bit later into the event, and I slowed everything way down because there's a lot going on in this that you probably don't even realize just by looking at it. So first, number one here, I already kind of talked about this, but you can see these wavy clouds here. This is the atmosphere trying to lift, but this area is capped off. And so we call a cap, it's basically just a blob of warm air aloft that acts like a lid. Thunderstorms can't form in it. And a lot of times when you have a front or something moving in that generates lift, you get these kind of wavy clouds, and you can see them from the ground too, as the atmosphere basically resists lifting and producing thunderstorms. So in this case, you have thunderstorms firing over here to the east, but over to the west, this is probably behind a frontal boundary, and this is stable air. So that's your first giveaway. This area right here with its bright, kind of really crisp clouds, those are updrafts. Those are thunderstorms forming. And as things get going, you can kind of see how it starts to look like kind of cotton candy that's been drawn out. That's the actual anvils of the thunderstorms, so the very tops of the thunderstorms being blown downwind by the jet stream, and they kind of get this kind of view going. The composition of the clouds will also change. These bright, really bright white ones are liquid water clouds. These ones are made of ice because they're so high up in the atmosphere. But basically, it's called glaciation is the process, and that's an indication that you have mature thunderstorms. Down here, you have this lovely little cloud street of north to south kind of little clouds here. This is actually warm, unstable air surging into the area where the thunderstorms are. And so this is actually the feeder process for instability, where you have this nice clear slot of warmth, and then you have the moisture streaming in there. So again, something you probably didn't even notice, but it's handy for this. And then over here, you have these, what look like really kind of strung out clouds. That's leftovers of old thunderstorms and then some new thunderstorms forming on the flank. So this is convective debris here, and then you can see another thunderstorm forms on the flank. Up here, this is all, we call it convective debris. It's all the anvil pieces, all the cirrus clouds. A lot of times during big severe weather events, when you have thunderstorms that form, these clouds upwind of the system can actually stop sunlight getting down and will actually cause thunderstorms to not form. It's pretty cool, but it also can kind of suck if you're out trying to spot and then these clouds come over and take away your sunshine and you don't get any severe weather. And then the final one down here, these are basically stratus clouds. Again, it's kind of the same thing that's going on over here. You can see little ripples. You can see the crisp kind of cauliflower looking clouds trying to form, but they're not really sustaining. So this is an area where you probably just don't have enough instability to support thunderstorms. So the main area is here and two, but there's a lot of other little things that you can pick out in the details of looking at this one image. So this is another example a little bit closer to home. This was the first moderate risk, which turned into a high risk for tornadoes in Iowa. And so this example here I really like because you can see the striations in here. There's a nice warm front parked, and this clear slot where there's warm temperatures into the north up towards Minnesota. Everything's all snowy. Combining satellite with radar is really handy, and it really kind of gives you further information. So in this example, you can see here, there's the really bright bumpy clouds. It's not a great example because it's kind of hard to see, but when you turn on the radar, you can really see that there is some good updrafts there. When you're looking at satellite imagery, oftentimes you kind of use it in tandem with other sources of data. So like in my day-to-day, I do this frequently. I'll put on observations of the different weather sensors, some model data. In this case, these are streamlines, so the way the air is moving. And so this example here is, you see the low pressure parked here. You can see this clear line basically really lines up well where there's a warm front parked. And so the question for severe weather will become, well, how far north does the warm front go? But you can see these little areas here. These are thunderstorms trying to develop already, cumulus clouds that are already bubbling. And so the atmosphere is going to go. It was a matter of deciding, how far north does the severe weather threat go? This is what the outlook was at the time I was, taking these observations. Again, the atmosphere is trying to lift and trying to go. It's resisting here, but south of this warm front, things are already starting to go, and that's why the Storm Prediction Center had a moderate outlook. So pretty cool stuff when you combine it all together. Another cool feature of these satellite products is that you can basically create sandwiches, they're called, combining different satellite bands. And so this is combining ice versus liquid clouds along with just visual imagery. And so the result is that you can see different areas of thunderstorms that are more intense. In this particular case, this is from 2019. This area that went right through just south of the metro produced tornado after tornado. I like this example too because you have all these other clouds, but because you're not looking for ice, you're only looking at the ice in the colors. The white clouds are basically low clouds, and so basically they're just clouds that could get in the way of producing severe weather. And I remember this event, there was some questions about how much the clouds ahead of the line would preclude tornado development. Turned out there's a lot of tornadoes to stay in, but in 2019, but or 2018, sorry, the Southeast Minnesota tornado outbreak, but pretty cool example, again, combining different types of satellite data into one kind of cohesive data map to look at things. A lot of times satellites can be really handy in what you might think are boring days. And so this is an example from 2021. It looks really messy. This is oftentimes, especially in spring, fall, winter in Minnesota, this is what things will look like. And so using those different types of bands to differentiate the types of clouds can actually be really handy. So this is using those different bands that will color the types of clouds differently. So the bright greens, that's actually snow on the ground. The light greens that you see up here, those are ice clouds. The yellow, or the white, excuse me, that you see here, these are liquid clouds. And then over here, these are clouds that are actually tall enough to actually get ice in them. So there's actually some convection going on over here to the right. There's some high clouds moving in, and there's some clouds on the ground. And that's why this looks so tricky to differentiate, but it's really handy, especially days when you have fog and things like that. You can use satellites to kind of parse that information out. It's not as fun as severe weather, but it is still pretty handy. And I also love this example where the snow's on the ground. You can actually see that cold air is inhibiting the growth of clouds. And so right in here and then back in here too, a lot of cool little physics stuff going on in here that I thought was interesting, which is why I picked it to put in the talk. Satellites, again, are very qualitative, and so you might just end up seeing a lot of other things by happenstance. So in this example, these are cirrus clouds coming in. It was a pretty quiet morning, and you can actually see contrails from jets in the cirrus shields. And we got quite a few calls at work about people who are concerned about chemtrails from these things. So that's why I included in the talk. The other thing to see over here is these are actually lake effect snow bands coming in off of Lake Superior. Pretty cool. You can see them in here too. And then the areas up in here where there's not much else going on, that's just snow on the ground. So even the qualitative satellite data can be really powerful. I kind of walked you through mesoanalysis earlier, but this is an example from Randy Bowers. Was at Norman and now at the Northern Indianapolis Weather Forecast Office. Basically talking about the different types of clouds and the environments that are spawning them. And so satellites can be really handy to kind of differentiate what's going on before a storm forms on radar. It kind of gives you the idea of where you, if you're a mobile spotter, where you might have the highest risk of severe weather. On the forecaster side, it lets you kind of pinpoint where a watch might be needed or what areas are at the highest risk for severe weather. Pretty cool stuff. I'd be remiss if I didn't talk about my other, day-to-day life with satellite. Air quality is really been helped out by satellites. Smoke from forest fires show up as more of this kind of gray, so we can actually watch that. I love this example because as the sun angle changes, you can actually see the extent of all of the smoke, which is basically all across the entire upper Midwest. We had the entirety of the state in an air quality alert at this time. I also love this example because you can see the lake breezes from Lake Michigan and Lake Superior kicking off clouds. So pretty cool stuff going on here, a lot of little small scale features, but GOES has specific bands for ozone, volcanic ash, and then smoke. So you can pick it out and use them for tracking different type of air masses. The thermal or IR window is also really handy for detecting wildfires. This is an example here. This black blob is a wildfire on 2020 near 35E and 35W split. You actually could watch it on the MnDOT cameras as we saw it on the satellite. This was the day where we had a red flag warning, and so we were concerned about if this fire would rapidly spread and cause any air quality concerns. And so the thermals can be really handy for picking that stuff out too. And some of the really big fires, they show up very well in the thermal window. You can also use the IR channels for tracking things like volcanic ash. This is the eruption in Hawaii from a little bit ago. You can see, again, the actual volcano lighting up with the magma and everything right here. And then on this side, you can see a little bit of the blue hue, which might be hard to see on your screen, but there's some blue hue in here that represents volcanic ash. And so you can actually track that. This is the only good examples I've had of volcanic eruptions since we've had these sensors around. It was pretty cool to see. But if you don't know, volcanic ash is really not great for aircraft. It kills aircraft engines. And so this was something that, that all different governments around the world are worried about. And that's why it's one of those things that the satellites pick up pretty well. So closing out the topics of satellites, I'd be remiss if I didn't at least talk about tropical cyclones. And so with this new super high resolution and super temporal resolution data, tropical cyclones, the forecasting and observation of tropical cyclones has completely changed. And so we basically had a lot of things that conceptually we thought we knew about the eyewall structures of hurricanes and typhoons. With this new data that updates every 60 seconds, you can actually start to see the mesovortices and things that we thought were there. We had numerical simulations on, but we can actually observe them now. And it turns out these little mesovortices inside the eyewall of the hurricanes is a major component of some of the wind damage you have. So this is Irma from 2017 when it was a Category 5 hurricane with 180 mile-an-hour winds, and so it was just kind of crazy to see the individual updraft pulses and the spiral rain bands, to see the mesovortices. This is one of the test cases for using GOES data, and it was, the first time we saw it was just crazy. You can also use satellite information to categorize tropical cyclones. So if you don't have any observations, they'll actually use the presentation of the storm on satellite to classify them, and that's how hurricanes are given a category when they're well out to sea. IR can be really helpful with tropical cyclones as well. This is Hurricane Matthew, and this storm was really interesting, not just because it's my namesake, but it had this really persistent blob of thunderstorms that kind of just coexisted with the core of the storm while it was a Category 5 hurricane. So this showed up really well in the satellite. You can obviously see the inner eye walls, but in the infrared, you can see the updraft pulses and these two blobs of thunderstorms. Really interesting structure, and I don't really know what caused it, but it's something we've seen in several hurricanes since. Something that I'm sure someone is researching. So before we go to our final question and answer, weather apps, I get a lot of questions about weather apps and what I use. I have GR, Gibson Ridge 2 Analyst, Radar Scope and Sat-Squatch are the ones I usually use, along with GR, Gibson Ridge Analyst 3. And then weather.gov. I can't say enough good things about weather.gov. They don't have an official app, and there's a lot of reasons behind that, but you can, make their website a button on your home screen, and that's what I do. Polling my coworkers and other meteorologists I know is Radar Omega has 3D radar, which is pretty handy. Windy, Weather Underground, which uses Weather Service data. Weather Bug, all of these are pretty good. On Android, I'm not as familiar. Pickle 3 was a fantastic application, but it's now dead. I think it's still around, but it's no longer being updated, but it was good. So this is what I use. Like I said, there's no really right or wrong answer. You just got to be careful of those the websites that offer mosaics and things, because you'll sometimes lose some important data. But even a mosaic radar data is better than having nothing at all to keep yourself safe. So some acknowledgements and where I got all these different images and everything from. Basically, a lot of crawling weather service sites and some journals and everything. So with that, I will be done now. A little ahead of time, but I wanted to leave some time for questions. I know people oftentimes have questions or something that they thought of while watching this. And so if you don't have any questions, thank you very much for your time and for watching. But if you do have questions, feel free to unmute yourself or type away. I have the chat box open here and can talk. So we have a question here from Liz. Sat-Squatch is actually a purely satellite-based app, which is really cool. And what Jarrod was mentioning, if you have Allison House, you can use your login to get data on that as well. So you can get observations and everything on top of satellite data. It's really cool. And so I love Sat-Squatch. It's one of those things where it's like, if we're out looking for auroras or something, I'll use it to keep track of cirrus clouds that might ruin it. But yeah, that's mine. We have a question here about Allison House feeds. Allison House feeds are great. They're the data sources themselves is straight from the Weather Service most often, and in my opinion, the best data that you can get. It's really handy. They work with a lot of different applications, and so I really like them.
The benefit of having a separate data feed like from Allison House and subscribing to it is that if most of everybody on here today lives in the metro, okay? If we have an outbreak, what's the first thing everybody does? They go to their phone to look at radar data, and when you do that, the pipelines getting to the Weather Service basically get bogged down. And so that public feed can sometimes lag or have issues. And so when it really counts as a spotter, what Allison House does is they have a direct line into there. And so there's a limited number of people that get that data. And so that means that you get that data even when the general public is not necessarily reliable. Do you have any example of a triple point, Matt? I see there's a question about somebody wanting an explanation or
the closest example I have in this deck is probably that first image. Oops, I'm going the wrong way. That first image in was this occluded front here that kind of washes that out. But if this low was connected to the warm and cold front right here without the occluded front, that would be a triple point. Where basically you have the combination of the lift from the low, the warm front, and the cold front that really is a very powerful mechanism to develop severe weather. And when you get storm systems that mature a little bit more, you'll have the secluded front, and this is still a decent setup for storms, but just not as compact and focused as the triple point is. So we had a question here about open data. Universities have been pretty good about it. Otherwise, a lot of websites, Pivotal Weather has been like my favorite. I use that both in and out of work. There's a lot of good free data you can get in there. The European stuff you need to pay for, but that's generally the best way to do it. Otherwise, you can use NOAA's data is all paid for by taxpayers, so it's all open to everyone. So those would be the best ways to get it. But there are a lot of vendors out there that will charge a lot for stuff that you can get free elsewhere. And so I usually look for NOAA, the National Weather Service data first, if not university. And if that doesn't work, there are some companies out there like Pivotal Weather that you can get some free weather data from.
Yeah, sometimes some of the state Department of Transportation sites have some free information. Another place that I utilize often is called Meso West. And they utilize like basically every single ground source observation network that's free. And you can look at any state. So you get more data points than you would just utilizing probably the most reliable weather service and airport observation stuff. There's some additional items in there that are included.
So how many GOES satellites cover the US? They have to be directly over the equator if it's geostationary. But how many satellites are in service for the GOES system?
Just two. Two in active service, and then there's one in standby. And the two GOES pass are basically one parked over in northern South America that covers the eastern half of the United States, and then GOES West covers the Pacific, Alaska, and Hawaii. And then GOES 14 is not the rapid refresh one like these ones are, but if something were to happen, it's still up there and can be maneuvered in. And it's still operational to as a backup if we needed to. So just the two, and then several other countries have satellites that will cover parts of the U.S. So Himawari from Japan covers the Pacific Basin, including California, Alaska, and Hawaii. I've used that from time to time, and then Sentinel, I believe, is the EU, covers parts of the Atlantic that you can use too. And so, yep, just the two from the United States, but a lot of the other countries' satellite data is available too online, and you can use it in tandem.
The WX app, it's not a Pickle 3 replacement, but I would consider it a less user-friendly experience, but you get a lot of free data and stuff there if you don't mind kind of figuring out what to look at and where to go. I actually have that on my phone too.
Let's see. Question here about positive and lightning strikes. I just put together a graphic for work. Lightning's tricky. So basically the ground is positively charged, and then as an updraft of a thunderstorm forms and things rub together, you get a negative charge inside the cloud. And so I have that backwards. The ground is negatively charged, and then you have positive strokes that come down to the negative ground. That's one path of lightning that you get a lot of. But what will happen is that to balance out those charges, the tops of the thunderstorms can become positively charged, and they become so positively charged that they're more positively charged than the positively charged ground. And then you can get what's called a positive lightning strike that comes from the very top of the thunderstorm anvil down to the ground. Those types of lightning strikes are 10 times more powerful than the negative strikes. And those are usually the bolts out of the blue types of things. But if you've ever been around lightning that like one comes out of the middle of nowhere, that's usually a positive strike. Or if you've been around lightning that has been like super loud and intense for no apparent reason, that's a positive lightning strike. And so basically it's just that charges get caught up at the top of the thunderstorm, have nowhere else to go. And so they come out of the very top of the thunderstorm down 50,000 feet to the ground. And that's the difference between a negative and a positive lightning strike. It's just the negative charge is closer to the ground. It's more connected. And one of the theories I read about ball lightning is because that positive strike is so much more powerful, you can create plasma and things like that around it. And that might be what ball lightning is, but we still frankly don't know what it is. Like there's a theories out there about what it might be, but no one's been able to like produce it themselves. So we still don't know. But that's the types of lightning strikes. Yeah, positive ones are scary. They're the ones that are the super loud, super intense ones.
Is there a difference between quality and paid and free apps? Yes, there is. So I think you'll find with the apps that we've mentioned, most of those are going to operate without flaws, and they're going to be kept up and user friendly on the platforms that they operate on. With those, the initial, there's usually an initial cost for the app. And depending on what you want to use it on, it may only be, $5-10. But if you want to use it on a computer, they may charge more for that as a one-time fee. And then most of them offer an additional service on there in different premium levels where you can subscribe monthly or yearly to get different things on there. So thanks everybody for coming out tonight. Well, if anybody else has any more questions, feel free to send us an email at training@metroskywarn.org. As well, we have our page for Metro Skywarn, which is specifically limited to the board and a few partners. And then for general chat, you can go to the Twin Cities Metro Skywarn group, which is more informal, which a lot of us are on that as well too, but you will get different perspectives and answers from various people on there.